Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and today we're going to look at another integral identity, an integral theorem that applies to field theory, and which in this case we'll make use of the curl as the underlying principle behind it. So let's start the notes as Modeling Methods in ME. And what we're going to study today is the so-called Stokes Theorem. And again, this is another integral identity like the Gauss divergency theorem. Now, in this case, the difference lies mainly into this usually a source of confusion as to when the Stokes theorem applies and when the divergency theorem applies, but the basic difference is that Stokes theorem applies over an open surface like this. So given this open surface in space, okay, not an enclosed domain like the Gauss theorem requires for it to apply. So given this surface and given a vector field V traversing it, and the closed surface is, the open surface is actually bounded by these lines C. So it's not a bounding surface, it's just a bounding line on the open surface. And remember that we can establish a window here, which we will call differential of that surface. And then there is a normal vector to that surface that may or may not be parallel to the vector field or perpendicular to the vector field. The vector field and that normal vector are obviously independent of each other. And then at any point on the closed contour that wraps the surface, we have these tangential vector S. So this is the tangent vector to C, to the closed contour line C. So this integral identity, and I'm not going to go through the demonstration of how we end up with it like I did for the Gauss divergency theorem, but it's through a similar process. The integral identity of the Stokes theorem indicates that the integral over the surface S, and remember this is not a closed contours or a closed surface integral, it's just a surface integral over these open, that's why there's not a circle here on this integral symbol, of the curl of V. So that is the underlying operation, vector operation on the field, dotted into the normal vector, differential of surface, equals the closed line integral. Now it's a line integral, that's the line that wraps this open surface, of V dr. And both sides of these integral are, as you can see, scalar quantities. The curl of the vector field is a vector quantity dotted into another vector that becomes a scalar, and on the right hand side we have a vector field dotted into dr, which also makes up a scalar. Now also recall that the line integral, the closed line integral of V dot S dc equals the closed contour or the closed line integral of V dr. So it's the same thing expressed in two different ways. You can say just the integral of differential of R over the differential of R, or you can just say V dot S as being the tangent vector to the line C, and that line C would just have to be parametrized to be able to integrate this. So dr is the differential position vector. So basically dr is equal to dx in the x direction plus dy in the y direction plus dz in the z direction in Cartesian coordinates. This is the differential of the position vector. So, given a vector field, V, which we usually denote as u in the x direction, v in the y direction, and w in the z direction, recall that the curl of v is equal to, we've already gone through this operation, so you take on the determinant of a matrix of d dx, d dy, d dz over uv w, and then take the determinant of that matrix, but that ends up being dw dy minus dv dz in the x direction plus du dz minus dw dx in the y direction plus dv dx minus du dy in the z direction. So the three components of the curl of a vector field. And let's say that S is given by this function z equals f of x and y. So let's say that we have a function that defines the surface S, and then we can establish the level curves of that function as f of x, y, and z is simply z minus f of x and y, and these are level curves because if z is equal to f of x and y, the lowercase f of x and y, then if we send this f to the left hand side, this will be equal to 0. So it's indeed a level curve. So we're defining a three-dimensional function out of a two-dimensional surface. So what we need to do is project, so I am sort of defining the process by which we conduct these integrals on the left and on the right. We're starting with the left hand side. Project or parameterize the surface S onto a plane A. And the way that works, so let's start by defining the Cartesian coordinates here, y and x. And let's say again, this is the surface, and we have the surface S, and this could be highly irregular, whatever is defined as f of x and y, which, by the way, we can also rotate, and for example, we can have a function y equals f of x and z. So it would be a surface defined along the y direction, or for which we could parameterize along the y direction. So this process applies the same exact way. And this is the curve C. So then this shape, the surface, can actually be parameterized onto, let's say, the xy plane. That will be ideal. If S is defined as a function of x and y, then we can actually project this down to the xy plane. And let's say that when you project this down, this looks like this shape, for instance. It's hard to see, but let's say that that's the shape that it projects down. So now this becomes, instead of a surface, it becomes an area, and it becomes an area on the xy plane. And this is also the line C that surrounds that plane. And let's draw a little surface here, differential surface, because remember, we're trying to perform an integration over the surface and then project it down. And then this would look like this. A differential of area xy, which is simply dx dy, or dy dx for that matter. It really doesn't make a difference. So when we project this differential of surface down to the area, so we're trying to perform this integration of our three-dimensional surface by projecting it down to the xy plane so that we can perform an area integral, which is much easier for us to do. The differential of surface is projected down as a differential of area through a Jacobian. And the Jacobian is nothing but a scale factor between the two differential of surface and differential area. So it's a scale factor between this curved differential of surface and this flat differential of area. So this is what's called a Jacobian. Also remember that the normal vector here, so we have a normal vector to the surface. The normal vector is grad of f divided by the magnitude of the grad of f, which is, if we use this particular definition of f, which is the level curves of the surface z equals f of x and y, it will just simply be minus df dx in the x direction minus df dy in the y direction plus 1 in the z direction. So we're just basically differentiating this with respect to x, to y, and to z. And then we're going to take the magnitude of this vector, and that's going to be the square root of df dx squared plus df dy squared plus 1. Okay, so those are the coordinates of this normal vector. We have to be careful as to whether that normal vector points out or in. Well, there's basically no out or no in, because this is an open surface, so there's nothing inside or outside. But depending on how we define it, we would have to select the coordinate or the direction in which we take the line integral for the Stokes theorem to actually be valid, because we might get the opposite of it, the opposite sign. So if the normal vector is actually defined in that direction, then the direction of integration of the right-hand side of the Stokes theorem has to be counterclockwise. If the direction of the normal that's selected points inwards into the surface, then the direction would have to be clockwise for Stokes theorem to match. Alright, so what else do we need in that integral? Well, on the right-hand side, we need to parameterize the curve C on the xy plane. Can be parameterized as, well, if we can place x as a function of t, y is a function of t, then z is equal to f, which is a function of x and t and y and t, such that t goes from some parameter a to b. So if we can somehow find an angle theta or a parameter t by which we can make this conversion or parameterization of the given function that defines the surface, then we'll be defining the line that wraps that surface. So in addition to this, then we can take the full differential of dc, and by applying chain rule, this would be df dx times dx plus df dy times dy. And furthermore, then we can say that this is equal to df dx times dx dt plus df dy times dy dt multiplied times dt. So we can take dt as a common factor outside, and then use this relationship between x and t and y and t of the parameterization to calculate these differentials and associate dx and dy to dt. If we do that, then the right-hand side, which is the integral over the line c of b dot dr, remember that dr is the differential of the position vector, and v is UVW, then this is essentially the integral over c of u dx plus v dy plus w dz. Remember, v is UVW and dr is dx, dy, dz in all three directions. Then by employing this parameterization, the right-hand side of Stokes Theorem, which is the integral over the contour over the line C of v dr, then reduces to the integral from a to b, the limits on the parameter t, of u plus w df dx times dx dt plus v plus w df dy times dy dt dt. So it basically becomes an integral of a single parameter t, becomes a one-dimensional integral, if we manage to parameterize x and y into the parameter t. Okay. Again, we go back to the left-hand side. This was the right-hand side. The left-hand side, we have the integral over the open surface S of the curl of the vector v, the vector field v, dotted into the normal vector, differential of surface. So the left-hand side becomes, so this integral, I'm just going to write it out. Is equal to the integral over the surface of the curl, which is dw dy minus dv dz in the x direction. I'm going to try to squeeze all these here. du dz minus dw dx in the y direction plus dv dy minus du dx in the z direction. That is the curl. So I'm missing the normal vector ds. All right. Remember that dA is equal to the Jacobian. Sorry, the S is equal to the Jacobian. The S is equal to the Jacobian times the differential of area. And for example, if we are able to project down to the xy plane, this will be the Jacobian in the xy direction and the area in the xy direction, the x dy or dy dx. In this case, the Jacobian in the xy direction is the integral, the square root of df dx square plus df dy square plus 1, where remember the surface is described by this function f of x and y equals e. Here's the Jacobian, and if you notice, the Jacobian is identical to the denominator. Go back here. It's identical to the denominator of the normal vector. So we can replace this differential of surface with Jacobian, which will actually cancel out with the denominator of the normal vector, and the normal vector will just simply be df dx and df dy and the x and y and 1 in the z direction. So then if we recall, the normal vector is minus df dx in the x direction minus df dy in the y direction plus 1 in the z direction. All of these divided by the magnitude of this vector, which is df dx square plus df dy square plus 1. And remember, f is the function that describes the surface S. is going to work out this way, so that the Jacobian denominator of n actually cancel out. So the left-hand side of Stokes theorem, which is the integral over the open surface of the curl of V dotted into n ds, works out to be the integral over the xy area, so it would be over limits in the x direction and the y direction, depending on how you write the x dy or the y dx, of the first component of the curl, which is dv dz minus dw dy. Notice that I am flipping that, negative of that, because this is going to be multiplying the f dx, right? And that was a negative number and the normal vector, plus dw dx minus du dz times df dy plus dv dx minus du dy. And that closes the brackets, and then the differential of area, which is dx dy, or dy dx. It's the same thing. So if you write dx dy, then the limits of integration of x will go in the inner integral, and the limits of integration of y will go in the outer integral. If you write dy dx, will be vice versa. So this is how you evaluate the left-hand side of Stokes theorem. All right. So now this is a generalization of how we evaluate Stokes theorem. That doesn't necessarily always apply, but in a sense, because remember that would all depend on whether we can actually parameterize the surface that we're trying to integrate over onto the xy plane. Sometimes that surface might be aligned with the y direction, or the function that we have is a function of x and z, so y equals a function of x and z. So whichever way we can express that, then we select the plane onto which we are going to project that surface onto a plane. So a slightly modified version of these expressions then is found, but the process by which you can find these expressions is identical. So let's look at an example. And this example, let's say given the vector field V is equal to xy and the x direction plus yz and the y direction plus xz and the z direction. Okay, so it's just it looks like a polynomial vector field. This is u, this is v, and this is w. All right, and the surface defined by, so we have the surface z equals 1 minus x squared, going from x from 0 to 1, and y going from minus 2 to 2. Then show or verify Stokes theorem. Again, this is an exercise on the obvious because Stokes theorem always works. We're just going to try to see if we can actually do the integrals on the left and on the right to be able to verify or confirm that it works. Now, what does this mean physically before we even get to these problems? Well, if you look at what Stokes theorem definition is, given a surface, and on the left hand side we have the curl of a vector field, which basically talks about the rotation of that vector field. So the vector field can actually be pretty straight, but it has some component of rotation, because rotation, remember, means whether the fluid particles traveling along the streamlines are rotating about their own axis. That's how we physically interpret the curl. Now, on the left-hand side, we have the rotation of the vector field, the rotation of these vector field. So imagine this vector field is a velocity. It's a flow field. Okay, it can be force, it can be energy, it can be anything, but let's just imagine it's a velocity field. So now we're talking about the rotation of that velocity field, and dotted into the normal vector. So the total quantity of rotation of the vector field dotted into the normal vector, integrated over that open surface, is basically the amount of rotation that the velocity field induces on that surface. That can be equated to the amount of velocity that actually circulates over the bounding line of that surface. So that's just the circulation. So the rotation equals the circulation. This is basically what the Stokes Theorem is saying. The net amount of rotation induced by a flow field is equal to the amount of circulation, to the net amount of circulation on the bounding curve of that surface induced by that vector field. So that's what the surface, Stokes Theorem is saying. This is what we're going to try to show in this example. Not that Stokes Theorem works, but try to see if we can find a kind of a physical interpretation of these, while verifying that it works by trying to solve these integrals correctly. So moving to another pad here. So let's try to draw what we have in hand. So this is Z, this is Y, and this is X. And remember, we also have, so we're going to go all the way to minus Y too, because the surface is defined by this with X going from 0 to 1 and Y going from minus 2 to 2. So let's say that this is 2, and here we have an equidistant away minus 2. It's sort of equidistant. If we plot the line Z equals 1 minus X squared, what we'll get is this. So from here, let's see, to here. So where this is 1 and this is 1. So when X is equal to 0, here, Z is equal to 1, and when X is equal to 1, Z is equal to 0. Okay, and that applies for all values, basically all values of Y. So this applies here. And let's do this here and parallel this. And let's do this here. So that same surface goes like this, and it also goes like this. So basically, the surface S, let's see if we can shade it, is that given by this upper surface right here. The line that surrounds that surface goes like this. So this is C. And if we define, let's say, a differential of surface right here with a normal vector. So this is the differential of surface, ds. That differential of surface will project down as a differential of area in the xy plane. So remember, ds is equal to j dA, and dA, which it looks like we can do in the xy on the xy plane, because this bottom is the xy plane, is dx dy, which is the same thing as dy dx, and the direction in which we define that will depend on how we can express the limits of integration. Okay, so let's look at the left-hand side of Stokes' theorem, which states that the integral of the curl of v dotted into n ds should be equal to the integral over the line c of v dot dr. So this should be equal to the right-hand side. And that's what we're going to try to prove. That if we take the integral over the surface, it would be the same as taking the integral of v over that line. So let's start with the left-hand side. The left-hand side says that the normal vector is the grad of f divided by the magnitude of the grad of f, such that z is equal to 1 minus x squared, and as you can see, this right here is f of x and y. There's no y, but that's still f of x and y, right there. And therefore, big F of x, y, and z is equal to z minus 1 plus x squared, which is equal to 0. So I'm going to take that entire thing, move it to the left-hand side, and find the level curves of that expression. All right. So here we are. So the gradient of f is equal to 2x. If I take the derivative of these, it's 2x in the x direction plus 0 in the y direction plus 1 in the z direction. Well, the magnitude of these, f, is the square root of this one squared plus this one squared plus this one squared. So it's 4x squared plus 1. And therefore the normal vector just works out to be 1 over the square root of 4x squared plus 1 times 2x in the x direction plus 1 in the z direction. Okay, that's how it works out. Again, there's no y component on these. Alright, let me go back. So we had some technical difficulties here with the recording. So just to recap, we had defined an example of Stokes' theorem as that given by the velocity field or vector field xy, yz, xz, and the x, the y, the z, and direction. And the surface defined by these parabolas, e equals 1 minus x squared, between 0 and 1 in the x direction, and between minus 2 and 2 in the y direction. We're to verify that the Stokes theorem is actually correct, which is, again, redundant because the Stokes theorem is correct. We're just going to try to verify that whether we can calculate this thing. So again, the surface defined by z equals 1 minus x squared is just basically a parabola in the xz plane. And since it says that it's going to be valid between y equals minus 2 and y equal 2, you just basically repeat that parabola along the y-axis. And basically the surface is the shaded area. That surface is bounded by this contour line C in that particular direction. Counterclockwise will allow to identify, or will allow to verify the Stokes theorem if we define the normal vector pointing up like that. That doesn't mean in or out, because as you can see, as an open surface, there's no in or out. But if we define the normal vector pointing up, then by the right hand rule, then the line C has to actually follow a counterclockwise direction. The differential of surface is equal to the Jacobian times the differential of area in the xy plane. In this case, we can take that surface differential and project it down to the xy plane. We can also do the same thing to the zy plane, same exact thing. If that's an alternative, then you can verify that that works as well. So basically, project this differential of area to the back wall and do these transformations exactly the same way. So we're going to verify that this left-hand side is equal to this right-hand side. Okay, the left-hand side of the Stokes Theorem and the right-hand side of the Stokes Theorem. So we start with the left-hand side. We calculate the normal vector. The curve is defined, the surface is defined by z equals 1 minus x squared. We define the level curves of that surface is c minus f of x and y equals 0. And z will be, capital F will be z minus 1 plus x squared. So basically take this to the left-hand side. The gradient of that will be 2x in the x direction, 0 in the y, and 1 in the x. And the magnitude of that is the square root of 4x squared plus 1. Those are the three components of the normal vector. Notice that there's no component in the y direction. That normal vector has no component in the y direction. It basically doesn't tilt in the y-axis. So always pointing along the parabola, either in the x or in the y, or has a component in the x and a component in the z direction, depending on where the point is along the surface. All right. Furthermore, well, we need to verify the left-hand side, or calculate the left-hand side of Stokes theorem, is the curl of the vector v. And the curl of the vector v is given by this expression, in which we take the determinant of this matrix, and we do so by augmenting it, as I just did here, multiplying the diagonals and subtracting the multiplication of the counter diagonals. So the curl of the vector v is equal to d dy of xz minus d, and if we go back in the x direction, d dz of yz in the x direction, plus in the y direction we have d dz of xy minus, if we go back in the z direction, we have d dy of xy. That's in the, in the y direction we have ddx of xz. ddx of xz. So that's that one. Plus, in the z direction we have ddx of dz of yz. This will be yz. So we have ddx of yz minus, in the negative z direction we have ddy of xy. So this one is 0, this one looks like 0, this one looks like 0, the dz of yz, so the curl of the vector v is minus y in the x direction minus z in the y direction minus x in the z direction. So it's the partial derivative of these expression with respect to c is just y. Partial derivative of these expression with respect to x is just minus c, and partial derivative of this expression with respect to y is just x. The Jacobian in the xy plane is the f dx in the xy plane square plus the f dy in the xy plane square plus 1. Such that, remember that the function that defines the surface is 1 minus x squared. So it's a function of xy, but there's no variability with respect to y. So and that's equal to z. All right. So the Jacobian in the xy, or on the xy plane, is equal to the square root of minus 2x squared plus 0 squared plus 1, and that just happens to be the square root of 4x squared plus 1, which always works out to be exactly the same as the denominator of the normal vector. So the differential of surface is the Jacobian on the xy plane times differential of area on the xy plane, which is equal to the square root of 4x squared plus 1 times dx dy, or dy dx. Or we could have done this in the xz plane, on the yz plane and on the back, and would have ended up with a similar expression. So let's go back to the left hand side. is equal to the integral over the surface of the curl of V dotted into n ds, which is equal to the integral over the area and the xy plane, curl of V dotted into n, Jacobian on the xy plane, differential of area on the xy plane. And if we expand this, just say this is equal to the integral over the integral on the xy plane. The curl, we already found out that was minus y in the x direction, minus c in the y direction, minus x in the z direction. We found that the normal vector was 1 divided by the square root of 4x squared plus 1 times 2x in the x direction plus 1 in the z direction. We found that the Jacobian was the square root of 4x squared plus 1, and this is dx dy. So this one, as you can see, always cancels with that one. And what we're looking for now is the left-hand side is the integral over the xy plane of this will go minus y times 2x minus z times 0 minus x times 1. So that would be minus xy minus x dx dy. Alright, so now we need to assign limits of integration in the x direction and limits of integration in the y direction. And in order to do that, again, we're going to look at what happens with this curve right here on its projection to the xy plane, because that's where we're integrating on the xy plane. So what we're going to do is we are going to plot this just on the xy plane. So on the x, let's just do it like this again, otherwise it'll get confusing. X, and again we go from 1 to minus 1 to 1, from 1 to 1. We go from 1 to 1 here, and we go from 1 to 1 here. As you can see, that is 2, that is minus 2, and now the curve projected onto the xy plane, let's use another color for these, is this is the area over which we're integrating. So we're basically integrating over a rectangle. That makes the selection of the limits of integration quite easy, because it's just basically constant limits of integration on both sides. So the left hand side would be the integral of minus 2xy minus x dx dy. We can also do dy dx, it makes no difference because the limits of integration in the x direction are from 0 to 1, while the limits of integration in the y direction are from minus 2 to 2, because we're integrating over a rectangle. So if we integrate that, we now have the integral from minus 2 to 2. Now let's integrate with respect to x, and if we integrate this with respect to x, we find minus x squared y minus x squared over 2, evaluated between 0 and 1, when x is equal to 0 and x is equal to 1, dy. and that would be equal to the integral from -2 to 2. So when x is equal to 1, these become 1, so that this would be minus y minus 1/2, and when x is equal to 0, then this disappears, dy. So the left hand side is equal to the integral of that with respect to y, which is minus y squared over 2 minus y over 2. Now this is evaluated between -2 and 2. So I'm going to take the minus 1/2 as a common factor, and this is y squared plus y evaluated between -2 and 2. So when we evaluate y squared at 2, we get 4. When we evaluate y squared at -2, we get 4, so that cancels out. So there will be y evaluated at 2 and y evaluated at -2, which is 4. 4 divided by -1/2, or 4 divided by -2. The left hand side just equals -2. So this is the contribution onto the rotation of the surface by this velocity field that traverses the surface. So the velocity field traversing the surface is making the surface rotate at a rate of -2, whatever those units are. All right. Now let's look at the right hand side. And on the right hand side, remember we have the integral over the closed line C of v dot dr, which is basically the integral over C of u dx plus v dy plus w dc. Right? And if we go back again and plot this, this is y, this is x, minus y. Again, I am going to go from here to here, from here to here. That is the surface S. And the line is just basically this line. And we're going to take the specific direction because we define the normal vector to point up like this. So I'm going to call this C1, C2, C3, and C4. For obvious reasons, because I cannot parameterize this curve into a single expression because we have these discontinuities here. And not discontinuities of the trajectory of the curve, discontinuities of the derivative of the curve itself. We have corners. So we're going to have to do 4 different parameterizations. Those are easy ones to do. Because notice here the function is just simply x equal 1 at y equals 0. So along C1, so this is 1, this is 1. Along C1, x is equal to 1. Z is equal to 0, and y goes from -2 to 2. Along Z2, we have z is equal to y minus x squared, and x goes, y is equal to 2, and x goes from 0 to 1. I'm sorry, from 1 to 0. So it goes in the reverse direction, from 1 to 0. In here, x is equal to 0, z is equal to 1, and now y goes from 2 to -2. So it goes in that direction. And along this direction, C4, then z goes like 1 minus x squared, y is -2, and now x goes from 0 to 1. 0 to 1. So in this case, actually x goes from 1 to 0. along C2. All right, so we just parameterize along those curves. So let's start with C1. C1, x is equal to 1, z is equal to 0, and y goes from -2 to 2. So that means that dx is equal to 0. That means that dz is equal to 0. So if x is equal to a constant and z is equal to a constant, those differentials are 0. And since y coincides with the y-axis, then dc is equal to dy along curve C1. All right. So the right-hand side along curve C1 is equal to the integral along C1 from of xy dx plus yz dy plus xz dz. And remember, we found out that dx was equal to 0, dz was equal to 0, and we also find that z is equal to 0. So all of that goes away. So that's 0. So there's no contribution of the rotation, the circulation of this flow field along that line. It doesn't circulate. So let's do C3. Let's do C3. We don't have to do this in a specific order. Let's do C3 because it's very similar. So in here, x is equal to 0, z is equal to 1, and y would go from 2 to -2. So this means that dx is equal to 0, dz is equal to 0, and that also means that dc along C3 is also equal to dy. So the right hand side along C3 is the integral along C3 of xy dx plus yz dy plus xz dz. Again, dc is equal to 0. We have x is equal to 0. It's also dx is equal to 0. And so x is equal to 0. So we have one term here that survives. Z is equal to 1. Y is equal to just y. So this is the integral from of y dy. Remember, z is equal to 1. So this one will go to 1. So, and the limits of integration now go from 2 to -2. And that would just be y squared over 2 between 2 and -2, which will be 0 as well. So there's no contribution of the circulation along the upper curve or the lower curve. All right. Let's continue now with C2. And hopefully we'll find some contribution, because we know that this has to equate the left-hand side, and the left-hand side gave us a number different than 0. So on C2 we have y equal 2, we have z equals 1 minus x squared, and we have x going from 1 to 0. So that means that dy is equal to 0. That means that dz, we can differentiate with respect to x, and this will be minus 2x dx. And then this is just dx. It goes from 1 to 0. So the right-hand side along C2 will be the integral over C2 of xy dx plus yz dy plus xz dz, where dy is equal to 0. This y here is equal to 2. And well, that's about it. And then we can replace z with these quantities and dz with these quantities. So basically the right hand side along C2 is equal to the integral along C2, which would end up being a differential of x from 1 to 0, for limits of integrations in x from 1 to 0, of 2x times dx this one goes away, or plus x times y minus x squared times minus 2x dx. And this is equal to the integral between 1 and 0. So if we expand this whole thing, this is the integral between 1 and 0 of 2x minus 2x squared plus 2x to the 4th dx. So I am just multiplying this out. So the right hand side along C2 is equal to, this will be x squared minus 2x cubed divided by 3 plus 2x to the 5 divided by 5, evaluated between 1 and 0, and that leads to a right hand side equals minus 11/15. Likewise, on C4, let's see if we can do this in this space right here. C4, we have y equals minus 2, c equals 1 minus x squared, and then now the limits of integration in the x direction would go from 0 to 1. So that means that dy is equal to 0. That means that the z is equal to minus 2x dx, and that's it. So the right hand side along C4 is equal to the integral along C4, again, of x y dx plus y. Again, we had some technical difficulties with the recording software, but I'm just going to recap here. Now we're trying to take the line integral over the line that bounds the surface S, and again we can break that up into 4 lines. We cannot do so with a single line and parameterize it because there's some discontinuities here. So line C1, line C2, line C3, and line C4. We're going to go in that particular orientation, and we have to respect an orientation because we define the normal vector to go up like this, and therefore this will have to go counterclockwise because of the right hand rule. Alright, so along curve C1, you notice that x is equal to a constant, it's equal to 1, z is equal to a constant, so it's equal to 0, and therefore dx and dz are also equal to 0, and y will go from minus 2 to 2. If we do that, the right hand side, so the integral on the left hand, on the right hand side, which is u dx, v dy, and w dc, u, v, and w being the components of the vector field v, will be xy, yz, and xz. Dx will go to 0, x will go to 1, c will go to 0, and so on. Everything disappears from this one. Then when we do the same along C3, x is equal to 0, z is equal to 1, and now the coordinate y will go from 2 to minus 2. In that case, one of these integrals survives, and it's basically the integral from 2 to minus 2 of y dy, which also turns out to be 0 because it's y squared over 2, and when we evaluate it between 2 and minus 2, we get the same contribution, 0. The third integral, or the integral over C2, will be along the line 1 minus x squared when y is equal to 2, and x would go from 1 to 0 in that particular direction. And if we apply that, then this is, by the way, if z is equal to 1 minus x squared, then dz is equal to minus 2x dx. This will be equivalent to performing the parametrization. We're just parameterizing z as a function of x, and therefore turning everything in here into an integral of x. So basically when y is equal to 2, dy is equal to 0, and this will just simply be, and then z will be 1 minus x squared, and dz will be minus 2x dx, and that will turn out to be an integral in the x direction from 1 to 0 of 2x minus 2x squared plus 2x to the 4th. That integral will just simply be x squared minus 2x cubed over 3 plus 2x to the 5 over 5, which if we evaluate from 0 to 1, all the contributions at 0 will go to 0, and it will just simply be evaluating this at x equal 1, which is minus 11/15. The last portion of this integral will be at or on C4. So from x equals 0 to x equal 1 along the line c equals 1 minus x squared, when y is equal to -2. So y is equal to a constant, and therefore dy is equal to 0. Same thing, y is equal to a constant, dy is equal to 0. Z is equal to 1 minus x squared. So dz is equal to -2x dx. So the integral over the curve of v dot dr is u dx v dy w dz. Y is equal to a constant -2. dy is equal to 0. And all we end up with is -2 times x dx. And then x times z, which is 1 minus x squared, times dz, which is -2x dx. That's the parametrization of z into x. Now all we end up with is an integral from 0 to 1, so x will go to 0 to 1, of -2x, we expand this whole thing, -2x squared plus 2x to the 4th dx, and that is basically minus x squared minus 2x cubed divided by 3 plus 2x to the 5 divided by 5, evaluated from 0 to 1. So the right hand side along C4, is equal to, this contribution would be minus 19/15. If you evaluate this between 0 and 1. So basically, the right hand side, which is the contribution over C1, C2, C3, and C4, where remember C1 and C3 gave us 0, C2 gave us minus 11/15, and right hand side over C4 gave us 19/15, is equal to minus 11/15 minus 19/15, which is minus 2. So essentially, the left hand side equals the right hand side, and therefore validating, not proving, but validating the Stokes theorem. I say not proving because this only proves the Stokes theorem for this particular vector field and for this particular surface, right? But it does validate that it works for this particular case. So this is what I wanted to go over today, just the definition of the Stokes theorem, which is again, interpreting it physically, is just a relationship between the rotation of a surface and the circulation that the vector field induces over the bounding curve. And we just went over a general procedure as to how to go about evaluating those integrals on the left and on the right, and a specific example of how to do it for a very specific case. So with that, we end for today, and I'll see you in the next class. See you later.